I wish to welcome you to today's ECT STAR introductory colloquium on science topic of the workshop, Strong Interactions from QCD to New Strong Dynamics at the LHC and Future Colliders. This workshop is part of a series that is sometimes held at ECT STAR. It was planned for 2020, but has been deferred to 2021 because of the COVID-19 pandemic and will focus on QCD phenomena at the highest possible energy scales. As you know, the intention of this colloquium series is to introduce and publicize the science case of the workshop to a wider audience. Today's presentation will be given by Marcel Foster, who is an experimental physicist in the Particle Physics Institute Fcce in Valencia, Spain. He's active in the ATLAS experiment at the LHC and the ILC and CIC projects for the Linear Electron-Positron Collider. His work focuses on jets and the top quark and on silicon detectors for charged particle detection. Dutch by birth and education from University of Utrecht in Twente, he is a staff member of the Spanish Research Council. Marcel, thank you for agreeing to give this talk.
Yes, welcome to this colloquium about the strong interaction at the LHC, the Large Hadron Collider, and future facilities, among which hopefully a Higgs factory and even beyond that. Before I start with the colloquium itself, I would like to thank ECT STAR for the invitation to do this, and of course for hosting our workshop on the strong interactions in recent years. This year, thanks to COVID, we couldn't have the workshop, we couldn't go to gorgeous Trento. And this colloquium tries to fill in that gap a bit. We try to bring the subjects of that workshop to a broader audience. So I'll be taking you on a tour through the Large Hadron Collider physics program with some emphasis on the strong interaction. And I'll give you a brief feel of what could be the roadmap for facilities beyond the Large Hadron Collider. I hope you enjoyed the tour. So what the mission of this field of science is to try and understand the fundamental constituents of matter. So what lies at the heart of everything that we see, all matter, including ourselves. Brian Cox said it better than I can. It is really the most fundamental understanding of the stuff that makes up all of us. We know there are lots of materials in our world, but there are structures, there are regularities, and already more than a century ago, people tried to order this in terms of what we now think are 180 stable chemical elements. We can organize thousands of materials in a smaller subset of elements. There is more than that. Within that table that you all know, there is a structure. We could try to understand that better. The chemistry that deals with combinations of these elements is a correct theory, but you can dig deeper and try and understand where those regularities come from. And at that point, you will develop the atom, the model of the atom that we discovered at the start of the century. Now we have only three basic components. We have a neutron, we have an electron, and we have a proton. And with that, we can put them together in different combinations, and we can reproduce all that complexity that is in chemistry with just those three elements. Now, you can dig even deeper, and that's what we will be talking about today. So this is a rough view of the constituents of matter and the particles that transmit the interactions between them. There are quite a few more than 3 elements at this point. But with this fundamental set of constituents, we can describe all the complexity of all those levels above particle physics. So you can make a hierarchy of these subjects. Chemistry sits on top. The atomic physics comes under that, and particle physics is deeper still within the nucleus of the atoms. Of course, you're probing smaller and smaller distance scales and higher energy scales as you go that route. A lot of jokes are made in science about which is the most fundamental science, but there is this hierarchy. So chemistry is applied physics, if you want. Biology sits on top of that. Psychology comes, sociology, politics, etc. Everything can be built up from that fundamental set of laws of nature. So the standard model as we know it, I've shown you a table with the elements. This one is a bit more formal. There are quarks. Those form the nuclei of atoms. There are leptons. The electron is one of them, but there happen to be more than just the electron. And then there are a number of gauge bosons which transmit the interactions. So the photon is responsible for the electric interaction, electromagnetic. The gluon is the force carrier of the strong interaction, and a W and a Z boson exist for the pretty weak nuclear force. The Higgs boson is special. It's not a force carrier per se. The Higgs field permeates all of space and gives mass to W and Z boson and also to the other constituents of the standard model. So we are quite certain, in fact, that this picture is essentially correct. But we're also certain that it's not the end of the story. So the standard model is both a successful theory that describes nearly all of current observations, but it's not the theory of everything. It doesn't include gravity, for one. It can't explain some phenomena that we see in cosmology, in rotation of galaxies, etc. So there must be more to it. So the goal of fundamental science is to discover a yet more fundamental theory that lies beyond the standard model. So let me introduce how we got to this point. So the photon is the one particle that you can detect because you have, right, the human body is equipped with a very good particle detector for photons in the visible spectrum. So photons are familiar. Then the electron, it was discovered early in the 20th century in what could be a precursor to an accelerator. There's an electric field, it accelerates electrons, they start to glow. These were known as cathode rays, and people discovered that was caused by a particle, the electron. The positron was discovered in cosmic ray experiments. So people would put a detector somewhere on the surface of the Earth, in this case in Caltech in California, and see what natural radiation they would pick up. And some of the electrons they saw were the wrong sign, and they were interpreted as antimatter. We have, for each particle, we have an antiparticle. The partner of the electron is the positron, and it was discovered in this type of early measurements. The same type of measurements gave a surprise. The same group, in fact, discovered something that nobody had ordered. The muon, as we now know, is a heavy copy of the electron. So we have a second generation of particles for every particle that we need, the up and down quark and the electron and its neutrino. We need those to build ordinary matter. But it turns out there's another set of quarks and yet another one, and there's a heavy electron and an even heavier one. It's the tau. We don't quite know what this structure points at. We observe it, it's clearly established, but we don't quite know why it's there or why the masses are the way they are. So these cosmic ray experiments were clearly very exciting. In the early days, people would go on balloons, go into the Alps and sit as high as they could on a mountain peak to find more and more cosmic rays. There's a cosmic ray experiment nowadays on the International Space Station, and it's still doing quite exciting physics. But at some point, roughly around the 50s, accelerators took over. So people learned how to accelerate particles in the lab, first with electrostatic accelerators. The cyclotron was born in Berkeley in the 30s. And after the Second World War, groups started to build accelerators that could accelerate particles in two opposite directions and then collide them. So that's the point where colliders were born. And these made very rapid progress. This is the beam energy, so which energy can we achieve in the lab as a function of the year. First, the electron-positron colliders made exponential progress through a decade. In the 80s, proton colliders took over, pioneering work at the ISR, at CERN, and since then the big discovery machines have been proton, antiproton or proton-proton colliders. And that gave us that table. So we have done experiments at increasing energies and gradually scooped up one particle after another to complete that table. I've listed the years and the places where things were discovered. We now have a complete set of experimentally established particles that make up this table of the Standard Model. So now we move to where we are today. And today, the frontier of high energy physics is the Large Hadron Collider at CERN in Switzerland. What you need is a little canister filled with protons. That's a surprisingly small canister. But then whatever comes after that is really quite large. We need a 27-kilometer tunnel to accelerate the protons, one proton in one direction, the other proton in the other direction, and we end up colliding them. The main technology in this machine is 8 Tesla dipole magnets. Superconducting technology. This didn't exist. This had to be developed for the LHC to be able to do its physics program. So it's really big science. We try to answer big questions, and you can't do them with small experiments. So it's 27-kilometer machine. The timelines are quite enormous as well. We had the first workshop on the LHC in 1984. First data was, operation started in 2010. And the LHC has a life until 2040 with several upgrades. It's a big investment, of course. Collaborations are very large. We do science now in groups of 3,000 authors, which is a whole different way of doing things. Fortunately, we'll see that these big efforts lead to big rewards as well. So the LHC has a number of experiments. I'll focus on the biggest ones and really mainly on the 2 general purpose experiments, ATLAS and CMS. But there is also LHCb and ALICE that I'll touch on very briefly, and there are a number of smaller experiments on that. So these experiments surround the interaction points where the protons collide and try to detect as much as possible of the sprays of particles that are produced. We have different subsystems specializing on different types of particles. So we have muon chambers that pick up the muons that have traversed all the other detectors. We have a special system that detects the energy of photons and electrons. We have a tracker system that can follow the trajectories of charged particles in a magnetic field. And piecing all that information together, we can hope to infer what happened in that proton collision. So the ECT star workshop that we're trying to make this a proxy for is about the strong interaction, that is the interaction between quarks. So I'll start from that side of things, which is not how the story is usually told. And in fact, most LHC events are governed by the strong interaction and are in fact quite simple. The protons have quarks and gluons inside. These bounce off each other and take off into the detector in a different direction. Now, you'll never see a quark or a gluon alone. It will form a spray of stable particles that we call a jet. And this is the type of events that we see most abundantly. This is an event display. When our last run started in 2015, this was the highest energy event that anyone had ever seen, 5 TeV out of the 13 TeV that the LHC produces. And you need to see 2 sprays of green lines, big energy deposits in the machine, in the detectors beyond that. So this is a dijet event, as we call it. And these are very useful for a number of things. The first thing we do when we switch on the machine is look if there's anything unexpected. And what we reconstruct is the invariant mass of those dijet events, and we see if some heavy new particle is produced and then decays in 2 jets. Now, unfortunately, the answer is no so far, but we do extend the limits on this type of new heavy states out to energies that no one had ever probed before. The previous colliders could reach a TeV. We're now producing events with 8 TeV. The LHC is really pushing that energy frontier well beyond 1 TeV. This is another view. You clearly see 2 highly energetic jets and some other particles in the event. We can do a more quantitative analysis. We can try and extract the magnitude of the strong interaction. And that is not per se predicted by the standard model, but the evolution with the energy, that is predicted. And we can compare measurements from lower energy experiments with measurements at the LHC. And in this figure, the blue points at the very highest end of the energy scale. Those are produced by Atlas recently. Each measurement is not the highest precision we've ever achieved on this quantity, but we probe out to a scale that no one has ever been at before. So again, there could be new physics, there could be a heavy colored object, and this evolution would change shape. We would evolve as the standard model predicts up to a certain scale, and then the slope would change. We haven't observed that. Again, it's a negative result, but we have been able to test this evolution out to scales that no one dreamt of before the LHC. Slightly more subtle and maybe harder to explain is the inside of jets. There is a structure to how the radiation is formed inside that jet. We use that structure to try and identify different types of jets. We can distinguish quarks from gluons, or a jet that contains a boosted W boson or a top quark from quark and gluon jets. We need the internal structure to do that, but it's something that is quite hard to predict. And one type of measurements we're doing today is measurements that we think of as auxiliary measurements. These give us a precise measurement of how the energy flow in the jet evolves. And we can compare that to our models, and we can try and refine the models, tune the models to data to make sure their predictions are as precise as we can. There's more. There's exotic QCD at the LHC. This is a result by the LHCb experiment. It's the only result I will show, with apologies to the flavor physics community. It really requires another colloquium to discuss all that's happening at LHCb and other flavor experiments. But one thing I wanted to show is a new exotic form of matter. Quarks are confined, according to our textbooks, in color neutral states. You'll never see a quark alone. There are two types in the textbooks. One is a baryon, so 3 quarks together can form a color neutral state and can live. A proton is an example. And the other option is to form a quark antiquark state. That would be a meson, like the kaon or the pion. And that's it. But we have evidence, and quite strong evidence from multiple experiments of that, for 4 quark bound states. So we're not quite sure what they are. These could be a type of molecules, a meson molecule. There could be genuine tetraquarks. The jury's not out on that, but their existence is firmly established, starting with the X 3872 that was discovered already a long time ago. Many more experiments found more X's, more Y's, more Z's. Many properties were measured, so we can try and come up with predictions that can be compared, and then we can try and disentangle between a meson molecule and a tetraquark. The latest in this is the LHCb announcement of a 4-charmed T tetraquark system. It's not completely clear what it is yet, but it's definitely exciting to see these new and unexpected peaks appearing in the data. And more exotic even, there's an experiment called ALICE that is devoted to studying heavy ion collisions accelerated in the LHC. So they will collide lead kernel and lead nuclei. That will give an enormous burst of activity in the detector. But there are collective effects that we can find, and we can find evidence for a new state of matter called the quark-gluon plasma that forms. And we are getting better and better at getting quantitative results, getting models that predict certain aspects better than others, and trying to understand how that hot plasma evolves. Again, this would need another colloquium. Apologies to the ALICE collaboration for not being able to dig deeper today. Then we go to other processes. We've talked about jets. There's a large number of processes that we expect to exist or even know to exist that we can measure precisely at the LHC. In fact, Paris Ficas, in his ICHEP 2020 summary, proposed that we change the name standard model to standard theory, because a theory that predicts as many observables, as many rates of processes correctly as the standard model is definitely more than a model. We have a long list of processes here. Some of them had been observed in previous experiments. Some of them are new. We see they span a long range of production cross-sections of rates. So when we want to look at the lowest lying processes with very tiny rates, we have to wade through all those other processes, make sure our selection is specific enough that we can see even the rarest processes. I'll highlight a few in the next lines. So first, let's look at known processes, but that are now available in incredible numbers. We have better theory than before. We have better detectors than before. We can now try and extract things more precisely from those known processes. One example would be W and Z production, another would be top quark pair production. These processes were discovered in the 80s and 90s. And now on a good day, the LHC produces hundreds of TT bar pairs a minute. And these can be used to go back to the magnitude of the strong interaction, alpha S, the strong coupling constant. We are now getting so precise in measuring these processes that the extraction of alpha S from these processes is competitive with previous colliders that ran in a cleaner environment with easier to predict processes. We are now competing with those, and the LHC still has a long way to go. Another example is the top quark mass. It's the heaviest quark in the standard model. We want to know its mass as well as we can, but people weren't particularly optimistic about our prospects. This article here that I quote is from 2002. People thought the top physics program of the LHC would be very quick. We produce so many top quarks that in a year or two we could do everything that we needed to do, measure the top quark mass to 1 GeV, and turn our attention to something else. That's not quite how it worked out. In 2020, we now have top quark mass measurements in several methods. The direct measurement reaches a precision of 300 MeV. Now, there are subtleties in the interpretation. We probably have to add 500 MeV to account for that, but there's good hope that we'll one day understand this measurement to the level where the experimental precision dominates. So we've gone a factor 3 beyond our wildest dreams already. There's another set of measurements that doesn't have as much problems with the interpretations. That reaches 700 MeV. So even that type of measurements that wasn't contemplated as very competitive back then is now better than we hoped we would be. So this is, I think, a testament of the incredible power of the LHC, the imagination of its users, progress in theory. We are now able to surprise the people that proposed the LHC. Another use that I don't think anyone realized back in the days before the LHC. There's a long-standing discrepancy. It's not very significant. It's about 2.7 sigmas. From the previous colliders. Lab measured W decays to electrons, muons, and taus, and found they don't quite agree. The taus are a bit off. Now, that is a long-standing issue, and Atlas has been able very recently to isolate a large sample of W bosons in top quark events and measure these rates again. We find a value that's exactly compatible with the standard model, and the precision is better than the combined lab experiments. But the LHC can discard this persistent test tension in the lab legacy with a measurement that no one had really foreseen before. Then there are genuinely new processes. These are things that no previous collider has been able to produce. One example is what we call top plus X. There are a number of processes where we produce top quark pairs or single top quarks in association with Z bosons, photons. No collider could produce these in sufficient numbers. The LHC can. We're now starting to constrain the electroweak couplings of the top quark to a precision that is still not competitive with how well we know the QCD interaction of the top quark, but we're improving very rapidly here. Another process, we're on the verge of discovering this, we hope, for top production. Atlas has an observed significance of 4.3 sigma, so not too far to get to 5 sigma where we can claim a discovery. And this process is not just bookkeeping. We want to measure as many processes as we want, because every process is special in how it probes new physics, possibly. This process has a vertex where 4 top quarks interact. That could be mediated by a new object that we have never seen. It also probes the top Higgs interaction in a special way. So all these processes bring us new information about the standard model, or about what might lie behind it, depending on the value that comes out. And of course, it's a good excuse to remember the 4 tops. Finally, we get to what the claim to fame of the LHC, the Higgs boson. We were convinced that something like a Higgs boson had to exist. We could predict, depending on its properties, how it would show up in the detector. Now, it's quite a hard process to detect. The Tevatron, the previous collider, produced thousands of Higgs bosons, but couldn't isolate a significant signal. The LHC produces many more, and then very clearly identifiable final states, such as this 4 muon final states. They really stand out when you select the data. So even a very tiny rate of Higgs production and Higgs to 4 muon decays, it can be picked up by our detector if we work hard enough. And indeed we did, of course. 2012, we announced the discovery, and that was based on a few channels. We now have the same plot, if you want, from 2020. The signal has grown. The blue Higgs signal sticks out much more clearly above the background. And there's no doubt that the discovery was real, of course. But again, we've extended the Higgs program in quite significant ways, and I'll try to summarize that in one slide. So it's clear already from how we saw it that this thing that we saw must be a Higgs boson. It must have some relation to the electroweak symmetry breaking mechanism. If it is the Higgs boson, the standard model Higgs boson, which is the simplest way to write down the Higgs mechanism, we know exactly how it must behave. So there are a number of production channels that have to appear. There are many different decays that we can observe. When the Higgs boson was discovered, Fabiola Gianotti, then spokesperson of the ATLAS experiment, said that nature had been kind to us because the Higgs mass is such that many of these channels can be probed at the LHC, and indeed the experiments have lived up to that promise. After the initial discovery, which was Higgs to ZZ, Higgs to photon-photon, and Higgs to WW, we found evidence for Higgs to tau-tau. The tau is a fermion, it's a heavy electron, if you want. So we now have evidence, and quite solid at that the Higgs couples to fermions, and that gives us confidence that it is indeed responsible for giving mass to the fermions. 3 years later, 2018, we saw Higgs to BB bar, the bottom quark decay of the Higgs. This is the dominant decay mode, but it's very hard to observe. We managed, now we know the Higgs couples to quarks, and it's likely that it gives mass to quarks as well. We saw different production mechanism, associated production with a vector boson fusion production, and in the same year we observed the top quark associated Higgs production. Now the top quark and the Higgs are very tightly connected, so that's an area where we're keen to get precise data, and we now have a very good probe to study that interaction directly. In 2020, we have evidence, not yet a discovery, we have evidence for Higgs to muon decay, and that's the first time we observed the Higgs coupling to the second generation. Now, we're not quite there. We have 3 sigma in CMS and 2 in ATLAS. but with data coming in the next decade, we're quite certain to be able to pin down this decay as well. So we're gradually mapping out the interactions of the Higgs boson, and we find that so far, with the precision that we've achieved, it does behave as the Higgs boson should. We have seen the couplings to all these different particles. They lie on that straight line that indicates proportionality to the mass. The Higgs boson is, within uncertainties, compatible with the standard model Higgs boson so far. So yeah, how well do we really want to know the Higgs boson or any standard model particle? Remember, I've shown you tables from the particle data group for the W decay. That is now superseded, so the next edition will contain that atlas result. I want to point your attention to the Z boson. We have had what could be thought of as a Z factory, a machine operating right at the energy that produces Z bosons in great abundance. And we now have very precise measurements of many properties, couplings to other particles, the width to invisible particles, which is very important, its mass. We know the Z boson to exquisite precision. Now, we're not quite there yet for the Higgs boson, but we have started to assemble a data sheet like we have for the other particles, and some measurements are already incredibly precise. So we know the Higgs mass to better than a per mil. We are quite certain that its spin and CP properties are compatible with what is expected in the standard model. The rates to everything that we've observed so far match the standard model to the uncertainty of about 10%. But there are other numbers that we don't know very well at all. One crucial measurement is the observation of double Higgs production. We know that the Higgs must couple to itself. The way to demonstrate that is observing this double production. So far, we have a limit. We haven't observed it, and the rate must be smaller than 13 times the standard model. Now, we really want to make that measurement more precise. Another example is Higgs to invisible. That could hide dark matter that couples to the Higgs boson. Again, a very tight limit or an observation of Higgs to invisible decays. That is high on our wish list, and so far the limit is 24%. It's better than we've ever been, of course, but we really hope to make progress on these numbers. So far, this is how far we discussed the present. I hope I have convinced you that colliders are a key tool to first develop and now confirm what is a quite successful theory of elementary particles. We have established this standard theory. I do hope that the next step of science, fundamental science as a whole, is to break that standard model, and that will guide us to a more fundamental theory yet that lies behind the standard model. And experimental hints are very welcome at this point. Any anomaly, something that doesn't match the predictions, will be very important to start to pull from that string and try and develop that more fundamental theory. There are many avenues to do that. The LHC is a key part of it. Its luminosity upgrade, the high Lumi LHC, will maintain the role of the LHC for a very long time. But we have other probes as well. We have ultra-precise low energy experiments. We have specialist experiments that look for a very specific signature of new physics beyond the standard model. We look for dark matter everywhere we can, direct, indirect, at colliders. We have cosmology, we have a lot of measurements on the universe, cosmic microwave background, structure formation, etc. that can give us hints. There's a good hope to start from the other end. The problem with this animal is that gravity doesn't fit in. studying quantum gravity in special environments, black holes, gravitational waves. That might give another look at that theory, might give us hints. And one part of the menu of things that we can do is to build a new collider. But before we do, let's first see what the LHC will still have for us. So we have finished LHC Run 2 in 2018. We have collected 140 inverse femtobarn at 13 TeV. That's close to the design values of the machine. We are in a shutdown to consolidate the machine, to start digging for a future upgrade. And we hope to resume operation Run 3 early 2022 and double the data set by the end of 2024. Again, double the data set will give us bigger chances of looking at rare channels, get us better uncertainties on the processes that we've already seen. It will gradually push the frontier. Now, to keep on making progress beyond that, we have a plan that's called the High Lumi LHC. We try to step up the luminosity, the intensity of the collision rates by a factor 5, maybe even 7.5, and then run for another period so that we reach 3 or 4 attobarns, inverse attobarns, at 14 TeV at the end of the 2030s or in 2040. That is 20 times the current data set. So in a sense, you could say that the LHC has only collected 5% of what it will be able to study at the end. And there are plans for new colliders. We had a long process to update the European strategy for particle physics, and similar roadmaps were drafted in China and Japan and the US. And the outcome of a long discussion is a quite concise and clear answer. What we need in high energy physics is an electron positron and Higgs factory as the next collider. That's the highest priority. It was not easy to reach consensus among scientists, it never is. But this one, everyone seems to agree on. Now, it's a bit more complex than that. You should never trust a one-sentence summary of a big political document. So I've included the links you can see for yourself. What is a Higgs factory, really? It is an E+ E- collider, electron-positron collider. It's operated at 250 GeV, which is right at the hill of that red curve there. That's what we call Higgs Strahlung. It's a process where we produce Z boson. The rate peaks exactly there, so 250 GeV is the right energy to run it at. And that can produce approximately 1 million Higgses. Now, that's not more than the LHC produces. The LHC, in terms of pure rate, is a better Higgs factory than this one. But the difference is that at a Higgs factory, the conditions are really nearly perfectly controlled. Let me try and explain that a bit better. E+ E- collisions have several advantages. One thing is that we know exactly what happens. The E+ and E- annihilate. They transfer all the energy to the system that we form, so we know exactly what should be the kinematics of that final state. We can build better detectors at future E+ E- collider because there's less radiation, less rate of jets. So we can focus on improving the performance. Machine-induced backgrounds are nearly negligible at a Higgs factory, while pileup and underlying event for the experts limit LHC analyses to some extent. One important one is that the standard model background, so other processes that look like the Higgs, are much more rare at an E+ E- Higgs factory than at the LHC. So we really have to dig through orders of magnitude of background events before we reach the Higgs at the LHC. At an E+ E- collider, that's much easier. And a theory advantage, it's much easier to predict the rate of Higgs boson production at an E+ E- collider to good precision than it is at the LHC. Now, what it will look like, the Higgs boson peak will appear as I show in this little picture here. It's a very clear peak. The background is not very large and can be controlled quite well. And the important thing is that we've reconstructed this peak on simulated events without actually touching any of the Higgs decay products. So just from looking at the Z boson associated with the Higgs boson, we can know where the Higgs boson is. Then we can easily count its decay products. And that's ideal for precision Higgs coupling measurements. But the electron-positron collider that we build, if we build one, is much more than just a Higgs factory. One can do a lot at E+ E- colliders. One plan is to repeat the run at the Z pole that I've mentioned before, but with an enormous rate. That's what we call giga or tera Z, and it allows us to do ultra-precise electroweave measurements. The 250 stage is the Higgs factory. I'll come back to that. Above 350 GeV, top quark pair production switches on. And we've never observed a top quark at an electron-positron collider before. We would really like to measure its properties as precisely as we can at the next E+ E- collider. Even higher energy, if we reach 500 or 550 GeV, we start to produce Higgs bosons in association with top quarks or double Higgs processes. And these are two key couplings of the standard model that we really want to measure as precisely as we can. There are plans for even higher energy E+ E- colliders, and those, their main raison d'etre is exploration. We want to go out to as high energy as possible to see if there's something new there. In a nutshell, you could look at this figure and you see the thresholds for the different processes. As we reach higher and higher energy, we can cover more and more of this physics. Now, the European strategy says build a Higgs factory, but it doesn't tell us how to build it. In fact, there are several projects. Some of them have been around for a long time, some are more recent. They fall in two categories. There's the linear colliders. The ILC project that I work on is one of those. And there, the selling point is to do 250 GeV as well as we can. But the main strength is to be able to go above to higher energies, to 1 TeV for the ILC, for clicks even 3 TeV. Their luminosity performance increases as we go to higher energy, so they start to shine more the higher we go in energy. There are two projects for circular colliders, CEPC and Fcce. They're very similar in design. The main difference is one is in China and the other one is proposed by CERN. These are circular machines. They're excellent at low energy, and then the luminosity performance degrades somewhat as you go up. So their program focuses on that Tera Z run at the Z pole. It does the Higgs physics, and Fcce even stretches to produce top quark pairs as well. Now, each of these machines has pros and cons, strong points and weaker points. We've studied, of course, in detail to try and compare the potential of all these options. For the Z pole, as I've already told you, the sheer luminosity of a circular machine, this Tera Z run, is unbeatable for electroweak precision physics. You see the current, the expected bounds for high Lumi LHC. You see how the different projects add to that, and the best we can do is high Lumi LHC plus Fcce, that circular machine at CERN. That's the blue dot in the center. So we really improve the precision on these measurements by quite a bit. We go here. Now the Higgs couplings, and that is the central part of the program. There are large uncertainties in our extrapolations of current performance in our potential studies. Especially lepton and hadron colliders are hard to compare. They don't measure the same things. It's very hard to arrive at an apples to apples comparison. But we do see that all of these Higgs factory projects can do very well. I've listed the precision for the coupling strength to different particles in this little table here. And you see that they all improve on high Lumi LHC by quite a bit. And among them, there are slight differences, but mostly within uncertainties, I would say that all these Higgs factories are of similar potential for the Higgs coupling program. There's a difference, of course, in the Higgs self-coupling. I've told you that to produce 2 Higgs bosons at any plus or minus collider, we need to go to higher energy. That can only be done with the linear colliders. So in this plot here, we see direct measurements of the di-Higgs boson rate and of this self-coupling only for the linear machines, or when we include a very high energy hadron collider. I think this is a crucial measurement, and I do think that if we were able to get just one number to good precision, it will be this. But it turns out it's one of the hardest numbers to get at. The high Lumi LHC will struggle. It will see some indications probably. And even the new projects have a hard time measuring this to better than 10% precision. And every one of these projects hides a lot of details that I can't show in this colloquium or can be summarized in a single plot. My Higgs factory project is called the International Linear Collider. It does all these measurements that I've mentioned before, sub% precision for some couplings. We measure couplings that are very hard to measure at the LHC, but it does so by combining the 2 energies. So we need the 500 GeV run of the ILC to really make this program give the best results it can. And even in that case, you see that the LHC data remains crucial for some couplings. Muons and photons, these are such rare processes that they're probably better measured at the LHC, but combining our LHC and Higgs factory data, we can really constrain the whole system very well. Top quark physics, I didn't want to miss out on showing that. We know the top quark is interesting, it's important for its own sake, but it's also tightly connected to the Higgs sector. So really, if we want to do as well as we can on measuring Higgs couplings, we need to constrain the top electroweak couplings in particular. Now this plot tries to summarize where we are with that program today. Those are the brown bars, and how the bars get shorter, how the precision improves as we add the high Lumi LHC first, then ILC 250, and ILC 500. And you see by executing this program, we bring down all these precisions by 1 or 2 orders of magnitude. The Higgs factory run at 350 GeV at the TT bar production threshold is also the ideal way to measure the top quark mass. If we are confident that we can reach a few hundred MeV at hadron colliders, an E plus or minus machine can really dig down and go to tens of MeV, 50 MeV with all the uncertainties accounted for at max. So the big question now is, when do we start digging? When will we start building this Higgs factory, and where will it be? In a sense, it's the scientist's job is done. We've handed in our homework, we've done a lot of studies, and now it's politics to decide which one gets built. So the status is that CERN investigates the financial feasibility of the Fcce, and in particular its tunnel. CLIC, the other CERN proposal, is relegated to the backup plan if the feasibility should turn out not to be there. The Japanese government is dragging its feet a little, but it ought to pronounce itself on the ILC. We think that will happen soon, but with the COVID situation, things are a bit less certain at the moment. And if that would happen, if the Japanese government comes forward with an invitation, we would build this project as an international machine. The strategy document in Europe says explicitly that it would be compatible with a European strategy, and European physicists would wish to collaborate. The big outsider in this game is China. As I said, they have a project that's similar to the CERN plan for a circular A plus E minus collider. They are to announce a decision on CEPC. An exact date is not known. Hopefully all these pieces will come in the future. The process will converge with at least one Higgs factory operating on the planet. There is some discussion on whether it's desirable to have more than one. Apart from politics, there are some scientific reasons to do that. In particular, one circular and one linear machine would provide the optimal coverage of all the energies from the Z-pole to a TeV, and it would definitely execute the Higgs factory program, or the extended Higgs factory program, with the best precision possible. What's next? The European strategy wants to be far-sighted, and we think even beyond the next collider. So you could call this the next-to-next collider. Europe, together with international partners, should investigate the feasibility of a future Hadron Collider at CERN with a center of mass energy of at least 100 TeV. Now, there's a large synergy with their plan for an E plus E minus collider. The same tunnel would be used by both machines, like we did with LEP and the LHC. So it's important to understand whether this is the way we want to go in the long distance future, because it affects the decision on the plus or minus Higgs factory as well. So that would look like this. The LHC is a large machine. This would be humongous. It's a 100-kilometer circular machine. It would circulate protons under the lake in Geneva. As I said, the viability is under study at CERN. Also, China is interested in a similar machine, which is called SPPC in their case. So there are a number of challenges to this. The first is to try and control the size and price tag of this machine. And the most promising way of doing that is developing cheaper or more powerful magnets. We're looking at new superconductors, niobium-3 tin, high-temperature superconductors, to see if we can get the same acceleration in a smaller machine, or maybe in a cheaper machine. The European strategy for particle physics also recommends that we intensify accelerator R&D. In part, that is that magnet R&D that I mentioned. But there are also resources being found now for novel accelerating techniques. One proposal is a muon collider. Muons are unstable, so it's very hard to build a collider, but their higher mass than the electron will give a real competitive edge if we manage to do this. There's some renewed enthusiasm here, but there are many challenges, and I hope in a few years, by the next strategy update, we will be able to tell whether this is a viable option or not. There's also a lot of progress in novel accelerating techniques, wake field acceleration, plasmas, or beam-driven new accelerators. A lot of progress is being made, mostly for applications that are not yet a high energy collider. Collider-specific work has been a bit more shy to ramp up, but there are groups working, Allegro and Awake are paving this way, and hopefully we'll be able to assess again whether one can build a Wakefield accelerator that brings us to an energy frontier collider in the next 5 years or so. So in summary, high energy collisions have been a fundamental tool to advance our knowledge of the constituents of matter. We know interactions of fundamental elements, mostly thanks to collider experiments. There were other inputs, and other inputs will remain to be important. But colliders are the best way to make progress in a controlled environment. The LHC program has opened the TeV regime. It has delivered a long series of discoveries, most of which you haven't heard about. But we've seen many previously unobserved processes. These were expected by the standard model, but our job as experimental physicists is exactly that, to confirm or discard the theory that we have by contrasting it with measurements. There's much more to come in the next 2 decades. We'll have more LHC. The luminosity upgrade will give it a lifespan to the 2030s. We'll hopefully see the start of operation of an E+E- Higgs factory. I can't tell you which one yet, but I'm confident that we'll converge on at least one option. And we'll intensify R&D on novel acceleration techniques to really guarantee a sustainable exploration of the energy frontier. New results will keep on coming out of the LHC. A way to stay tuned is to connect to these CERN feeds that I've listed here. But I'm sure if we make a major discovery, you'll hear it through the official press as well. Thank you very much for your attention, and I hope you enjoyed the tour.